In this lesson, you'll learn about propellers, their function and operation. Although we will, of necessity, very occasionally make mention of the aerodynamics of propellers, it is important you be aware that this is not a lesson on the aerodynamics of propellers. Propeller aerodynamics are dealt with in the subject Principles of Flight. The purpose of a propeller is to provide thrust to drive the aircraft forwards through the air. This is achieved by accelerating a comparatively large mass of air rearwards, thereby producing forward thrust. A propeller consists of two or more aerodynamically shaped blades attached to a central hub. This hub is mounted onto a propeller shaft which is driven, either directly or indirectly, by the engine. The hub and the blades are thus spun round by the propeller shaft, and act rather like wings, which by rotating would generate lift, or in this case, thrust. In order to be able to explain how a propeller works, it's necessary that we use a certain amount of terminology. Like a wing, a propeller blade has a root and a tip, a leading and trailing edge, and a cambered cross-section, whose chord line passes from the center of the leading edge radius to the trailing edge. The cambered side of the blade is called the back, while the undercambered side is termed the thrust face. Where the section of the blade becomes round at the root area is termed the blade shank, while the base of the blade is called the blade butt. The propeller blade is set into its hub so that its chord line forms an angle with the plane of rotation of the whole propeller. This is called either the pitch or blade angle. The theoretical distance, ignoring slippage, that a propeller or propeller blade moves forwards when the propeller shaft has completed one rotation is called the geometric pitch. All propellers, however, lose a certain amount of efficiency due to aerodynamic and compressibility losses. As a result, the geometric pitch can never be achieved. The actual distance that the propeller moves forward during one revolution is called the effective pitch. The efficiency loss, that is, the difference between geometric pitch and effective pitch, is known as slip. The efficiency achieved will usually be in the range of 80 to 90%, and can be found by using this formula. The path of the propeller blade through the air, which describes a helix, determines the direction from which it will receive its relative airflow. This helical path is the resultant of the propeller blade rotational velocity and the aircraft forward velocity. The angle between the relative airflow, the actual path the blade describes through the air, and the chord line of the blade is called the angle of attack. The angle of attack is kept quite small, usually between 2 to 4 degrees. As the blade rotates at this small, positive angle of attack, a thrust force is generated, very similar to the way in which lift is generated on a wing. Because the rotational velocity of any point on a propeller blade increases with increasing distance from the center of the hub, so the magnitude of the thrust generated at any point along the blade would also increase with this distance, if the pitch of the blade remained constant along its entire length. If the blade pitch remained constant along the length of the propeller blade, the increase in force developed by the outer part of the blade, compared with that developed at the slower moving blade root, would tend to bend the blade as depicted here. The angle of attack depends on blade angle, the rotational speed of the propeller, and the forward speed of the aircraft. To keep the angle of attack within necessary limits along the length of the blade, we therefore reduce the blade pitch from root to tip. This has the effect, when the aircraft is in flight, with the propeller rotating at its designed operating RPM, of maintaining a fairly constant thrust force along the length of the blade. We've just seen that a propeller receives its relative airflow from a direction which is governed by the aircraft's true airspeed in the direction of flight and its own rotational velocity in the plane of rotation. The operating angle of attack will be the angle between the relative airflow and the chord line of the propeller blade. This chord line is set at an angle to the plane of rotation, which, as we've already seen, forms the blade angle or the propeller pitch. From this animation, it can be seen that an increase in true airspeed will reduce the angle of attack, whereas an increase in rotational velocity, or RPM, will increase it. At high true airspeed and low propeller RPM, for instance with the aircraft in a power-off dive, it's possible to reduce the angle of attack to 0. While at low true airspeed and high RPM, for instance in the climb, it's possible to stall the propeller blade. Both extremes are obviously inefficient and therefore undesirable. The conclusion that must be drawn is that for a given fixed pitch, a propeller will only work efficiently at one combination of true airspeed and RPM, as is shown in this diagram. The propeller designer will attempt to ensure that peak efficiency is achieved at cruise true airspeed and cruise RPM. When a fixed-pitch propeller is being driven by a piston engine, the RPM is dependent on both the power setting, throttle position, selected by the pilot, and the true airspeed of the aircraft. It would be possible to overspeed the engine in a dive if the throttle was not closed. Conversely, with the aircraft stationary on the ground, it may not be possible to achieve rated RPM with the throttle fully open. Because of all of the disadvantages of the fixed-pitch propeller that we have just mentioned, advanced piston engine aircraft are fitted with variable pitch, constant speed propellers. This type of propeller is able to operate efficiently over a wide range of airspeeds. The power setting of a piston engine is defined by a combination of manifold pressure and engine RPM. Where both a separate power lever and a propeller RPM control are provided, it's possible to vary one of these parameters while leaving the other to remain constant, so optimizing the operation of the engine-propeller combination to give the best efficiency and fuel economy, while reducing the engine wear and tear to a minimum. In order to achieve this, a variable pitch propeller is used. The system changes the pitch angle of the propeller blade to vary the load on the engine, thereby maintaining the selected RPM of the engine-propeller combination independent of manifold pressure, provided that the propeller is operating between its fine and coarse pitch stops. The fine and coarse pitch stops may be fitted internally or externally, depending on the make of the propeller. Once an RPM has been selected, a control unit, either a constant speed unit or propeller control unit, will automatically vary the propeller blade pitch angle, and therefore its angle of attack to the prevailing relative airflow, in order to maintain the selected RPM despite variations in airspeed and manifold pressure. Variable pitch propellers may also have a reverse pitch and/or feathering function, the advantages of which will be discussed later in this lesson. This animation shows that under normal propeller control conditions, it's possible to provide a range of propeller pitch angles ranging from max course, cruise, all the way through to reverse pitch. The alpha, or constant speed range, is used for normal flight. It includes all pitch angles from flight fine through to max course, while the beta, or ground range, includes pitch angles between flight fine and maximum reverse. The feather position is not included in either range, and is used for emergency conditions only. In the event of engine failure, the propeller blades will be moved directly to this position to prevent windmilling. There are no pitch angles available between max course and feather. The method of control within the alpha and beta ranges and the means of achieving the propeller feather position will be discussed progressively throughout this lesson. Varying the pitch of a propeller throws up two basic problems, one of blade actuation and one of pitch control. We will initially examine the problem of blade actuation. The issue of pitch control will be covered later in this lesson. Although mechanically or electrically actuated pitch change mechanisms are in use, the hydraulic method is the most commonly used. The system utilizes oil from the engine or reduction gearbox lubrication system as the source of hydraulic pressure. In this system, the pitch change mechanism is operated by a piston moving under the influence of the oil pressure. Use the up and down arrows on your keyboard to change the pitch of the blades on this propeller. Hydraulic pitch change mechanisms can be one of two types, single-acting or double-acting. A single-acting propeller has oil pressure applied to only one side of the piston. The return movement of the piston requires the force of a spring or sometimes compressed gas. A double-acting propeller has oil pressure applied to either side of the piston in order to move the propeller between the two extremes of fine and coarse pitch. Whichever type is used, the flow of oil to and from the actuating piston is controlled by a propeller governor. Dependent on the propeller manufacturer, the governor may also be known as a constant speed unit or propeller control unit. In addition to controlling the propeller pitch angle, the unit normally incorporates a small oil pump, which increases the oil pressure to the value required for system operation. A single-acting propeller is constructed basically like any other variable pitch propeller, in that the blades are arranged round a central, engine-driven hub with the cylindrical hydraulic pitch change mechanism mounted at the front. The pitch change cylinder, or dome, contains a movable piston which is activated by boosted engine oil pressure. Movement of the piston will rotate the propeller blades towards either coarse or fine pitch. Typically, rotation is accomplished by a mechanical linkage attached to the rear of the piston, which operates an actuating pin machined on the butt of each blade. The actuating pin is offset in order that it can impart the correct range of angular motion. Generally, blade rotation towards coarse pitch is induced by an internal spring or gas pressure, and or counterweights attached to the blade roots. Most single-acting propellers, however, will utilize both a spring and counterweights. As we said earlier, some systems may use compressed gas instead of the spring. In feathering-type propellers, the spring has a dual function. It assists the counterweights in driving the propeller blades towards coarse pitch, and, when selected by the pilot, it actuates the blades into the feathered position, when engine RPM is low and there is insufficient centrifugal force acting on the counterweights. The constant speed unit, or CSU, incorporates a valve, which, because it has lands or grooves cut into the operating portion of its stem, is called a landed valve. This landed valve controls the flow of oil to and from the propeller actuating or pitch change cylinder. A speeder spring acting above the valve tends to force the valve downwards, while a set of flyweights driven by the engine oppose the spring and act to lift the valve. An input from the pilot's RPM lever or propeller condition lever will adjust the setting of the speeder spring, selecting the RPM which the CSU then automatically maintains. In order that it can respond to the various demands made by the pilot regarding the propeller RPM, the constant speed unit controls the oil flow to the pitch change cylinder in three ways. If the propeller is underspeeding, then the flyweights will be leaning inwards because of the reduced centrifugal force, allowing the speeder spring to push the landed valve downwards. This will allow the unit to supply oil to fine off the pitch of the propeller, causing an RPM increase. If the RPM is as required, in other words the propeller is on speed, then a hydraulic lock is formed in the system, maintaining the blade pitch constant. If the propeller is overspeeding, then the flyweights will be forced outwards by centrifugal force, compressing the speeder spring and allowing the landed valve to move upwards. This will allow oil to drain back into the engine system. This type of double-acting mechanism used on larger propellers, like the one shown here, achieves control of blade pitch angle by means of a hydraulically actuated piston connected to a cam slot, which rotates a bevel gear. The bevel gear engages with and drives other bevel gears located at the butt of each blade. Oil flow to either side of the piston is controlled by a propeller control unit. Alternatively, the type of control system shown here has a similar pitch change mechanism to the single-acting propeller. Like the single-acting propeller, its pitch change mechanism is also mounted towards the front of the hub, and the cylinder also contains a hydraulic piston. However, in the double-acting system, this piston will have hydraulic pressure directed to either side of it. Fine pitch oil is sent to one side of the piston, or coarse pitch oil is sent to the other. This eliminates the need for coarse pitch springs or gas pressure, and, with the exception of some larger propellers, the assistance of centrifugal counterweights. The double-acting propeller's controller will respond to the various demands made by the pilot regarding the propeller RPM to control the oil flow to either side of the piston in the pitch change cylinder in three ways. If the propeller is underspeeding, then the flyweights will be leaning inwards because of the reduced centrifugal force, allowing the speeder spring to push the landed valve downwards. This will allow the unit to supply oil to fine off the pitch of the propeller, while simultaneously porting coarse oil to return. The piston will move to fine off the blades, causing an RPM increase. If the RPM is as required, in other words the propeller is on speed, then a hydraulic lock is formed which traps oil both sides of the piston, maintaining the blade pitch constant. If the propeller is overspeeding, then the flyweights will be forced outwards by centrifugal force, compressing the speeder spring and allowing the landed valve to move upwards. This will simultaneously allow coarse oil to be ported to one side of the piston and fine oil to drain back into the engine from the other side. The piston will move to coarsen the blade pitch, causing a decrease in RPM. A constant speed propeller must be capable of all the pitch change operations mentioned previously, as they are selected by the pilot moving the RPM lever in the cockpit. The system must also be capable of maintaining a selected RPM within its own operational limits, regardless of changes in airspeed, altitude, and engine power setting. When the constant speed unit senses that the RPM is as has been selected, the system remains in a static state. However, any change in airspeed, altitude, or engine power setting will result in a tendency to either increase RPM above or decrease RPM below the value selected. As we've seen already, a tendency for RPM to increase, an overspeed condition, will be countered by a supply of oil being fed to the coarse pitch side of the piston in the pitch change mechanism. As is shown in this animation, the pitch will then coarsen and propeller torque will rise as a result of the increase in the blade angle of attack. Propeller torque now exceeds the engine torque and will cause the RPM to decrease back to the selected setting. As the RPM regains its previously selected value, the movement of the landed valve in the constant speed unit, which directed the oil flow in the first place, is progressively reversed until it regains the sensitive position, where a hydraulic lock holds the position in the pitch change mechanism immovable until the next RPM selection or disturbance in airspeed, altitude, or engine power setting. A tendency for the RPM to reduce, which is termed a propeller underspeed condition, must be countered by a supply of oil being fed to the fine pitch side of the piston in the pitch change mechanism. As is shown in this animation, the pitch will then fine off and propeller torque will fall as a result of the decrease in the blade angle of attack. Propeller torque is now less than the engine torque and will cause RPM to increase back to the selected setting. As RPM regains its previously selected value, the movement of the landed valve in the constant speed unit, which directed the oil flow in the first place, is progressively reversed until it regains the sensitive position, where a hydraulic lock holds the piston immovable until the next RPM selection or disturbance in airspeed, altitude, or engine power setting. Should an engine fail in flight, its propeller control unit would sense a drop in RPM, and, in an attempt to maintain the pilot's selected RPM level, would move to the underspeed or fine pitch position. Centrifugal moments acting on the blade would cause it to rotate towards fine pitch. This would result in the propeller being put into a windmilling situation, with its pitch change piston abutting the fine pitch stop. The immediate result of this would be a very large asymmetric drag, which would yaw the aircraft violently towards the failed engine. A second possibility, if the propeller continued to windmill and drive the engine, could be a complete mechanical breakdown of the engine, and even an engine fire. So, to minimize drag, and also to prevent further possible damage to the engine and the aircraft, some propellers, particularly on multi-engined aircraft, are provided with a means of turning the blades edge-on to the air flowing over them. In this edge-on position, where no aerodynamic force is generated either forwards or backwards, the propeller will cease to rotate. This action is called feathering the propeller. If the engine had actually failed, there would be no requirement to unfeather its propeller. However, propeller manufacturers usually provide an unfeathering facility, by means of which, if appropriate, an engine restart may be attempted. This may be a requirement following asymmetric flight practice. The operating principle of the propeller control unit incorporated in a feathering propeller is similar to that previously discussed, in that the unit contains an oil pump to boost oil pressure delivered from the engine or reduction gearbox, and a hydromechanical governor for RPM control. There is, however, the addition of a feathering mechanism, the operation of which will be discussed progressively throughout the lesson. Control units with feathering mechanisms may be found on both turboprop or reciprocating aero engines. Dependent on the manufacturer and type of propeller system, the controller may be known as a propeller governor, a constant speed unit, CSU, or a propeller control unit, PCU. For the remainder of this lesson, we'll refer to the unit as the Propeller Control Unit, or PCU. The controls available to the pilot are again dependent on type. Most spark ignition piston engines and many turboprop engines are equipped with a twin-lever cockpit arrangement, whereby the pilot has separate engine power and propeller control levers. In this arrangement, propeller feathering can be manually achieved by moving the propeller control lever to the feather position, or on some aircraft by means of a separate feather lever. Some turboprop engines utilize a single lever arrangement, whereby the pilot is provided with a power lever only. In this arrangement, propeller pitch, RPM, and engine fuel flow, power, are simultaneously adjusted. Feathering may be achieved by moving the engine high-pressure fuel cock to the feather position. New generation reciprocating engines equipped with Full Authority Digital Engine Control, or FADEC, also use a single lever arrangement, whereby the pilot selects the required power setting and the propeller pitch angle is controlled either electronically by an electronic engine control unit or by a hydromechanical control unit. This diagram illustrates that the propeller control unit may contain a number of components which are additional to the basic constant speed system that we discussed earlier. The feathering mechanism provides a means of manually lifting the landed valve to the overspeed or coarse pitch condition when the appropriate control is moved to the feather position. The actions required to feather a propeller are dependent on the type of engine and propeller combination and the type of aircraft they are installed in. For single-acting propellers, this normally involves moving the propeller condition lever, or RPM lever, to the feather position. Moving the appropriate lever to the feather position mechanically lifts the landed valve against the speeder spring to its highest position, thereby simulating an exaggerated overspeed condition. The landed valve will remain in this position until the feathering control is moved back to its normal position. Any oil in the pitch change cylinder can now drain away, allowing the spring or gas pressure, assisted by counterweights, to move the piston onto the feathering stop. To unfeather the propeller, the speeder spring tension is released by moving the propeller control lever to a position comparable to that of the serviceable engine, which of course is running at normal operating RPM. This moves the landed valve down and connects the reserve oil pressure line to the fine pitch side of the propeller pitch change cylinder. A reserve of oil pressure may be supplied by means of an accumulator, which is charged continuously during normal operation. By activating a release valve, oil pressure from the accumulator is directed to move the pitch change piston to fine pitch. Alternatively, some systems may utilize an electrically operated unfeathering pump, or on some smaller systems, the engine may require motoring over on the starter to build up sufficient oil pressure. Once the propeller blades have moved away from the feathered position, the propeller will start to windmill, and as long as the engine has fuel and ignition, it should start. When an engine, which is fitted with a single-acting propeller, is shut down after flight, the propeller should be at the fully fine pitch position. There is a considerable quantity of oil trapped under pressure on the fine pitch side of the piston in the pitch change cylinder, which is holding the propeller in the fully fine position. This oil pressure is being opposed by the force of the feathering spring. After engine shutdown, the trapped pressure will gradually leak away past the landed valve in the constant speed unit. As this trapped hydraulic pressure leaks away, the feathering spring is able to slowly push the propeller blades towards the fully feathered position. While this condition would be acceptable to a turboprop with a free power turbine, it would result in an unacceptably high loading on the starter motor of a piston engine or direct coupled turboprop. So, to prevent the feathering spring pushing the blades all the way to the feathered position, on those engines where a feathered propeller would cause stress on startup, centrifugal latch pins are incorporated in the pitch change mechanism. The latch pins are held disengaged by centrifugal force while the engine is running. As the engine RPM reduces, small springs behind the latch pins overcome centrifugal force, and they are allowed into contact with the piston mechanism. Typically, the value of the RPM at which the latch pins become engaged is around 650 to 700. After engine shutdown, the latch pins engage with a groove in the piston mechanism, which locks the piston. This prevents it from being pushed beyond a predetermined blade angle, and further into the feathered position by the feathering spring. When the engine is started and RPM increases, centrifugal force will disengage the latch pins. Fine pitch oil will quickly build up and hold the propeller against the fine pitch stop. Note that if a propeller engine combination does have a centrifugal latch mechanism fitted, it may become impossible to feather the propeller of that engine once its RPM has fallen below the latch setting value. This is because once they are engaged, the latch pins can prevent the piston being moved any further by the feathering spring. It is thus extremely important to complete the feathering drill before the RPM decays below this figure. Double-acting propellers do not have springs or gas pressure to assist in changing propeller pitch. Thus, all of the actuation, both to fine and coarse pitch, must be hydraulic. Engine or reduction gearbox oil is once again used as the hydraulic medium for this purpose. The inset diagram of a dry sump oil tank, which you may remember was used previously in the lesson on engine lubrication, illustrates how a protected source of feathering oil is provided. The oil pressure required for feathering the propeller is generated by an electrically driven pump, which may be activated by a feathering button in the cockpit. With the exception of operating the feathering pump, the basic control selection for feathering the propeller remains the same. That is, selection of the propeller control or condition lever, operation of a separate feathering lever, or, on some turboprop systems, moving the HP fuel cock to the feather position. For the purposes of this lesson, we will consider that we are feathering a propeller which has twin lever control. The propeller control lever is brought back through the fully coarse position to the feather position. Alternatively, where fitted, the propeller feathering lever is operated. This action lifts the landed valve in the propeller control unit upwards, thereby connecting the feathering pump oil line to the coarse pitch side of the pitch change piston, and allowing oil to drain from the fine pitch side of the pitch change piston. The feathering button in the cockpit is pushed in, energizing the feathering pump solenoid relay to supply the feathering pump. It also energizes the hold-in coil, which keeps the feathering button depressed for the time being. Feathering oil now passes through the ports of the landed valve, pushing the pitch change piston so that it moves into contact with the feathering stop. Oil pressure will now build up within the system, eventually operating a pressure-operated cutout switch, which will interrupt the supply to the feathering button hold-in coil. This causes the feathering button to release, which terminates the supply to the feathering pump solenoid relay, which in turn breaks the supply to the feathering pump. If the propeller is allowed to windmill, the forces generated will cause it to try to unfeather itself. Moving the propeller blades a few degrees below the feathered position will cause the propeller to rotate, and centrifugal turning moments will tend to move the blades towards a finer pitch. This will cause the propeller to rotate faster, until it comes under the control of the propeller control unit. The propeller control lever of the unit being unfeathered should be placed in line with that of the operating engine or engines, and where fitted, the feathering lever should be reset. This allows the speeder spring to push the landed valve down. It also helps to minimize the yaw which will inevitably accompany the effect of unfeathering. Pressure oil can now be directed to one side of the pitch change mechanism to move the piston towards a finer pitch, and coarse pitch oil will be allowed to drain from the other side as it does so. The feathering button should now be pressed. This starts the feathering pump running, which will supply the pressure oil to the pitch change mechanism to move the blades away from the feathered position towards fine. Once the propeller starts windmilling, the feathering button should be pulled out. Pulling out the feathering button overcomes the holding coil. When the contacts of the feathering button are opened, they break the supply to the solenoid relay, the contacts of which are supplying the feathering pump. Thus the feathering pump stops. The rest of the restart drill is accomplished in accordance with the aircraft operating manual. To reduce the workload on the pilot in the event of an engine failure, some propellers are equipped with an auto feather system. The system is normally active during takeoff and cruise conditions only. For example, on a turbojet engine, with the high-pressure fuel cock open and the power lever set to high power, a signal of low torque from the engine torque meter system will automatically feather the propeller. Should either of these conditions not be met, the auto feather system will be rendered inactive. This diagram shows an auto feather system installed on a typical double-acting propeller arrangement for a turboprop engine. It consists of an additional oil pressure line supplied from an electrically operated feathering pump to the underside of a valve lift piston in the feathering mechanism. Control over this oil pressure is provided by an electrically operated solenoid valve. In the event of an engine failure, and provided the engine controls are set to the high power configuration, a low torque signal will complete the auto feather circuit and energize the valve lift solenoid and feathering pump. This delivers an independent supply of feathering oil to the valve lift piston, which raises the landed valve to the coarse pitch position. The high pressure oil supplied by the feathering pump is now fed to the coarse pitch side of the pitch change piston, pushing it onto the feathering stop. As the piston moves, it displaces the fine pitch oil to return. The feathering stop is fitted within the pitch change mechanism, the position of which allows the propeller blades to take up a position edge-on to the aircraft airflow, where they will generate zero aerodynamic force in either direction. The propeller should not now windmill. The propeller control unit incorporates a flight fine pitch stop solenoid, which controls a supply of high-pressure oil to a flight fine pitch stop mechanism in the propeller pitch change cylinder. When the solenoid is energized, oil pressure is directed to withdraw the flight fine pitch stop, thereby allowing the pitch change piston to move below the flight fine position and into the beta range. When the solenoid is de-energized, oil pressure is removed, and the flight fine pitch stop is engaged by spring pressure. Use your mouse to press the repeat button, which will enable you to see the removal of the flight fine pitch stop again. Most turboprop engines are provided with a system of propeller control which is defined by alpha and beta ranges. The alpha range is used at high speed during the takeoff run, in flight, and during the initial high-speed part of the landing rollout. The alpha range is selected by moving the engine power lever to a position at or above flight idle. The beta range is used on the ground only. It's selected during the landing roll by first removing the flight fine pitch stop, or FFPS, which was previously engaged to prevent the blades moving to ground fine pitch in flight, and then moving the engine power lever to a position below the flight idle position. On systems not equipped with a hydraulic flight fine pitch stop, the power lever is moved through a flight idle detent or gate. With the propeller blades functioning within the alpha range, their pitch is controlled automatically by the propeller control unit, whilst within the beta range their pitch is controlled by the operator's movement of the engine power lever. In most aircraft, the selection of the beta range is made by movement of the flight fine pitch stop, the FFPS lever. Alternatively, in some systems the selection can be made via the condition lever, that is the RPM lever, itself. A warning light, usually blue or amber, illuminates whenever the flight fine pitch stop is disengaged. Additionally, other warning lights may be provided, which illuminate whenever the propeller blades are moved below the flight fine pitch position, that is, into the beta range. While the aircraft is taxiing, there is insufficient RPM available to bring the propeller control unit on speed, and it's therefore unable to take control. Propeller RPM is controlled by movement of the engine power lever within its range below flight idle. As power is applied for takeoff, the flight fine pitch stop lever is forced into the flight position by the action of moving the power levers to the takeoff power position. The FFPS light and/or beta lights are extinguished. As the pitch of the blades coarsens to allow the propeller to absorb the increased torque being produced by the engine, the piston in the pitch change mechanism moves into the flight pitch range or alpha range. This allows the flight fine pitch stop to engage under spring pressure, thereby preventing the piston from moving below the flight fine pitch position. There is now sufficient RPM available to bring the propeller control unit on speed and into a controlling condition. Many turboprop aircraft and a few high-powered piston-engined aircraft are provided with a means to allow the operator to select a superfine pitch, or to aerodynamically reverse the pitch of their propellers, or even in some cases to do both. In the case of a superfine pitch selection, a fixed abutment stop in the pitch change cylinder allows the piston to take up a position at or near 0 degrees. This is known as a disking position, and is used for starting and initial acceleration of the engine, and for aerodynamic braking during the landing roll. Superfine pitch is commonly called ground fine pitch, and its position is several degrees finer than the finest pitch available in flight, which is called flight fine pitch. The propellers of more modern aircraft may have a much greater range of blade movement in the beta range. The range can extend from around plus 8 degrees to minus 30 degrees pitch, which is full reverse. The beta range of this type of propeller is selected in a similar manner, and at the same point in the landing run as the previously discussed system, that is, during the high-speed initial part of the landing rollout. In this case, however, the braking effect obtained from the selection of reverse pitch is much more effective than that which would result from merely the selection of ground fine pitch. With the propeller in reverse pitch, the forces on the propeller blade are as shown here in the small diagram on the right of the screen. As you can see, in reverse pitch, the forces generated by the propeller will produce a braking effect to actively decelerate the aircraft after landing. On landing, the flight fine pitch stop lever must be moved to the disengaged or ground position before the engine power lever can be moved below flight idle. On systems not equipped with a removable flight fine pitch stop, the power lever must be moved through a fixed gate or detent. On some aircraft, microswitches, which sense that the weight of the aircraft is on the wheels, ensure that this selection cannot be made in the air. Once the power levers are moved below flight idle, the propeller blades move into the ground fine pitch range, and the propeller control unit relinquishes control. Propeller RPM is now controlled by power lever movement. The forward velocity of the initial landing roll combined with low RPM and low blade angle, produces a zero or negative angle of attack. This reverses the total reaction produced by the propeller, which acts to slow the aircraft in its landing roll. This condition is known as disking braking. Propellers which can have their pitch angle made even more negative are known as fully reversing propellers. As the power lever is moved further rearwards into the reverse pitch range, the blades move into the negative pitch position. The reversed total reaction produced now increases. This exerts increased load on the engine, so engine power is increased in order to maintain a constant RPM. The engine power and reverse airflow through the propeller is now being used to slow the aircraft down. This condition is known as power on braking. Many multi-engined aircraft are provided with a visual indicator, which is called a synchroscope, which indicates the RPM differences between the slave engines and the master. As you can see from this picture, the presentation consists of miniature propellers, which rotate to show when an RPM difference exists, and whether the slave is faster or slower than the master. In order to reduce the amount of vibration which can damage aircraft components, and also to reduce noise harmonics which can occur on propeller-driven aircraft, the engine propeller assemblies are often provided with a means of making the RPM of each unit the same as all the others. A synchronization system will reduce the annoying harmonics which can be produced by out-of-sync propellers, and also lower noise levels significantly. Electromagnets in the head of the rotating assemblies of the propeller control units of each engine are used to generate an RPM signal. An aircraft fitted with such a synchronization system will have a designated master engine, and other engines will be specified as slave engines. The signals from the propeller control unit of the master engine and those from the slave engines are sent to a control unit where they are compared. With the synchronizing system engaged, any RPM differences between the master and slave engines will be sensed in the control unit. The control unit generates proportional, positive or negative current outputs which are sent to torque motors. The torque motors are mounted on the slave engine propeller control units in such a way that a signal indicating that the slave engine is running at a lower RPM than the master will cause the slave engine's torque motor to turn in order to fine off its propeller, thus increasing its RPM until no discrepancy exists between the slave and master engine speeds. If, on the other hand, the control unit receives a signal indicating that a slave engine is running faster than the master engine, then it will send a signal to the appropriate torque motor to coarsen off the propeller blades of that slave engine to reduce its RPM, until once again no discrepancy exists between the slave and master engine speeds. So, the torque motor rotation resets the speeder spring on the affected slave engine's propeller control unit, which will ensure that it is once again synchronized with that of the master engine. When no difference in RPM exists between the master and the slave propeller, no output is sent to the slave torque motors. A more significant improvement in noise levels can be obtained by ensuring that adjacent propeller tips are separated by some optimum angle to prevent noisy interaction between them. This interaction is at a maximum when the propeller blade tips are opposite to each other, as is shown here. The synchronization system often also incorporates a synchrophasing feature that allows the operator to phase the propellers. Phasing is a means of adjusting the position of the blades on one propeller in relation to the blades of the one adjacent to it. The ability to phase can allow the operator to move much of the propeller vibration to unoccupied sections of the aircraft, thereby reducing the annoying beat of the propellers and providing additional comfort to the passengers. The systems of some aircraft provide the pilot with a means of manually fine-tuning this angle to obtain the quietest result. The more powerful an aircraft engine becomes, the larger must be its propeller if it's to absorb the torque output of that engine. Unfortunately, if the propeller diameter is increased as a way of increasing the size of the propeller, and the engine rotates at the same speed as it did previously, the propeller blade tips would be moving at sonic or even supersonic speed. This is very inefficient as well as being noisy and potentially damaging to the blades. So, if we have to use a large diameter propeller and yet maintain its RPM to a level that will not allow the tip speed to exceed that of the speed of sound, the propeller drive speed must be reduced to a more suitable level by a reduction gear placed in the driveline between the engine and the propeller shaft, as is this example of a Pratt & Whitney R4360 engine, which is shown as a cutaway. The parallel spur gear type of reduction gear, whilst being mechanically simple and relatively cheap to produce, takes up a lot of room at the front of the engine. This is because the axes of the gears are parallel. This system of reduction gear has been utilized mostly on V-type, inline, water-cooled engines, for example the Rolls-Royce Merlin and Griffon engines. The epicyclic reduction gear layout is quite compact and has the advantage of being a concentric layout. All of the gears rotate about the same center line. The gears themselves may be straight cut, beveled, or even helically cut. Helically cut gears are extremely efficient in the way they transfer power, and they are also very smooth and quiet in operation. They do, however, impart a degree of end thrust which has to be contained, usually through the use of thrust bearings. This end or axial thrust is proportional to the torque passing through the shaft of the gear. Axial thrust, as we'll shortly see, can be used to provide a torque indication system in a propeller reduction system. A torque meter can be provided to give the pilot information about the amount of power the aircraft engines are generating during any phase of flight. The instrument may be calibrated in units such as pounds per square inch, pounds-feet, Newton meters, brake horsepower, or any other suitable unit of power. Either electronic or hydraulic torque meter systems can be found in service. An electronic torque meter system, such as the one shown here, utilizes the angular displacement of a drive shaft, which is placed between the engine and the propeller drive. This displacement, being proportional to the transmitted power, is measured electronically, and the signal thus generated is used to drive the needle in the torque meter. This system is inherently lighter and more reliable than the hydraulic system. There are two types of hydraulic torque meter system, one which utilizes the end thrust generated by a helically cut gear, the other employs the torque reaction of a ring gear. They are both used to alter the oil pressure of the torque transmission system, which is then transmitted to the torque meter gauge on the instrument panel. This simplified diagram shows a ring gear system. When the engine is running, the pinions or planet gears are being driven around inside the stationary gear by the central engine crankshaft. The thrust reaction generated by the rotation of the pinions will try to rotate the stationary gear in the opposite direction to that of the pinions. The stationary gear is restrained by being attached to pistons fitted within cylinders that are being supplied by oil pressure, which is generated by a torque meter system pump. One of the pistons in the system partially covers a bleed hole, which, if it's uncovered, will allow oil pressure to be dumped to the engine oil return. While the engine is running, the piston in the cylinder with the bleed orifice will take up a sensitive position where the oil pressure generated by the torque meter pump just balances the thrust being generated on the stationary gear. If the engine torque increases, the piston will be driven, by rotation of the stationary ring gear, to cover more of the bleed hole. This will cause the oil pressure within the cylinders to increase until the piston moves back into the sensitive position, where torque meter oil pressure once again balances engine torque. The increase in oil pressure required to achieve this balance is indicated on the torque meter gauge as a rise in engine output torque. If engine torque decreases, the oil pressure in the cylinders will now exceed the pressure required to balance the torque output of the engine, which is acting on the stationary ring gear. As a consequence, the pistons, which were being maintained in a sensitive position by the balance between the engine torque and oil pressure, will now move to uncover more of the bleed hole. This will cause the oil pressure to decrease until the piston moves back into the sensitive position, where torque meter oil pressure once again balances engine torque. The decrease in oil pressure required to achieve this balance is indicated on the torque meter gauge as a fall in engine output torque. Engine torque is proportional to the horsepower being produced by the engine, and this is transmitted through the propeller reduction gear. The helical gear torque meter system depends upon the axial thrust which is developed when helically cut gears are used to transmit power through the propeller reduction gear. The shafts of the gears rotate within cylinders, and the axial thrust they develop is balanced by oil pressure trapped inside the cylinders. Torque meter oil pressure is transmitted to a gauge in the cockpit. The gauge is calibrated in pounds per square inch. The system oil pressure, which in some systems can have quite a high value, for instance the Proteus engine was capable of developing about 800 pounds of torque, is generated by a torque meter system oil pump. In this system, which is similar to that used on the Rolls-Royce Dart engine, there is an oil pressure bleed hole within each cylinder. When the thrust developed by the helically cut gear is exactly balanced by torque meter oil pressure, the shaft of each helical gear takes up a sensitive position, partially covering the bleed hole. If engine power output increases, the axial thrust being transmitted by each gear also increases, which forces its shaft further into its retaining cylinder. Thus the shaft is forced into a new position where it blocks the bleed hole. The torque meter oil pressure, being unable to escape, now builds up to a new higher value, until it's able to force the gear shaft back into the sensitive position, where once again it's able to balance the axial thrust being developed by the helical gear. If the engine power output decreases, the axial thrust being transmitted by each gear also decreases, which allows its shaft to be displaced slightly out of the retaining cylinder. Thus the shaft is forced into a new position where it uncovers the bleed hole. The torque meter oil pressure now falls to a new, lower value, until the lower axial thrust being developed by the engine is able to overcome it and force the gear shaft back into the sensitive position in the cylinder. Once this has happened, axial thrust is again balanced by oil pressure in the cylinder, but now it's balanced by a lower torque meter value. In addition to giving an indication of engine power output, the torque meter system can also be utilized to send signals to the auto feather and the water methanol injection systems. The auto feather system, as its name implies, will automatically feather the propeller of a failed engine. This is particularly important if the failure occurs on takeoff. The checks to be carried out on a propeller after engine start and the methods used will vary from aircraft type to aircraft type and from propeller type to propeller type. In addition to the checks which are described here, it must be remembered that there are many other checks which are carried out on propellers. Most of these checks are maintenance orientated, but nevertheless a pilot is still responsible for the pre-flight visual inspection of the propeller. The particular checks that we are about to examine are those for the single-acting propeller fitted to the Piper PA-34-200T Seneca aircraft. After engine start, the engine oil must be warmed up to the level required by the operating manual before any checks are commenced. The checks form part of the normal after start and before takeoff checks. For the sake of minimizing confusion between gauges, we, in this demonstration, will concentrate only on the left or number 1 engine. The first check is a part of the power check. The remainder forms part of the before takeoff check. Here we've highlighted the particular parts of the checklist that we are concerned with. Throttle, 1900 RPM. Be aware that you don't really want to use any more RPM than necessary. Propeller, RPM lever. Exercise. This part of the check ensures that the propeller functions correctly under the impetus of the oil pressure being fed to the pitch control mechanism. Check RPM drops when min RPM selected. Check RPM drops when min RPM selected. Pull the propeller control lever to minimum and allow the RPM to decrease by 200. At this point, it's not necessary to wait until the RPM falls to the absolute lowest possible value. You're only checking for the correct functioning of the propeller control system. Check RPM returns to 1900 when max RPM selected. Return the propeller control lever to maximum RPM and check that the RPM recovers back to 1900 as the propeller blades move back towards fine pitch. Repeat. Repeat the previous 2 checks again. By doing this, you'll ensure that warmer oil is being introduced into the propeller control mechanism and the associated pipework. The warmer oil will sharpen up the propeller's response to your movement of the propeller control lever. Throttle, 1500 RPM. Moving the propeller control lever back towards the white line on the control quadrant with this power set should not elicit any RPM change at all, because the propeller is within the constant speed range. Propeller feathering. Check. Moving the propeller control lever below the white line will cause the propeller blades to move towards the feathered position and the RPM to decrease. If, as is the case with the propeller we are considering, a centrifugal latch mechanism is fitted, it's important that the RPM should not drop below 1000, because the centrifugal latches will not become engaged and the propeller will feather, which is not what we're trying to achieve in this check. Throttle. Close and set 1200 RPM. Initially the throttle lever should be closed and the slow running RPM checked at between 7 to 800 RPM. Then the throttle should be set to obtain 1200 RPM. At this RPM the engine should run smoothly and the spark plug should not oil up while you're carrying out the checks on the other engine. Propellers. Max RPM. Select the propeller control lever to the maximum RPM position. Propeller de-icing. As required. If icing conditions expected during or immediately after takeoff, select On. Check propeller de-icing ammeter. Check both alternator ammeters. If your aircraft has double-acting propellers fitted, then the checks to be carried out are much the same as those for an aircraft fitted with single-acting propellers. There will, of course, be differences in detail concerning the basic RPM settings, etc., but the object of the checks will be the same, that is, to ensure a rapid and accurate response to RPM control lever movement. As with the single-acting propeller, It's necessary, once the lubricating oil in the engine has warmed sufficiently, to exercise the pitch change mechanism. This will evacuate the cold, sluggish oil from the pitch change cylinder and purge it from the constant speed unit and the associated oil passages. Just as happened with the Seneca checks, once the oil temperature is increased, there will be an engine test procedure for the double-acting propeller, which will involve causing the pitch change piston to travel from the fine pitch stop to the feathering stop more than once. With a double-acting propeller, there is not only double the amount of actuating oil in circulation, but also an extra system to check. The correct performance of the feathering pump will have to be ascertained, along with the functioning of the pressure-operated cutout switch. This concludes the lesson on propellers.